So far, with hypothesis testing and confidence intervals, we focused on differences in proportions. This was a good place to start, since a controlled trial is always a difference in proportions, and a controlled trial is one of the most fundamental ways to design a research study. But there are other types of statistics. We are now moving on to just a single proportion instead of a difference between two proportions. So what kind of statistic is this? Well, it is a proportion, a percentage, but only one. We're asking about the value of a single percentage observation. It is still a categorical variable with two options. It's like a trial, but without a control group. There is only the treatment group. So instead of comparing the two groups, it's just about the one group. What percentage of the group falls into the two categories? Regardless of the two categories, they are generally interpreted as success and failure, and we will use that language throughout. What kind of questions are we asking then? Well, we're asking these questions. How many Canadians support the Green Party? There's only one group, Canadians, but there are two categories, support or do not support. There is one percentage. What is the percentage in the category support? How often do we have snow in September at Edmonton? There is only one category, years, and there are two outcomes, snow or no snow. And that leaves us with one percentage. How many years have snow sometime in September? How many restaurants in Edmonton have gluten-free options clearly available on their menus? There again is one group, restaurants in Edmonton, and there are two categories. Gluten-free options clearly available or not clearly available. And then there is one percentage. How many restaurants have this? Here's the example we're going to work with. A survey of payday loan borrowers asked 826 people if they supported better regulation on payday loan lenders. 578 responded yes, which is 70%. Our sample statistic is 70%. The question for a single proportion is almost always a threshold one. Here, say we want to know if the population parameter, that is, the percentage of all possible payday loan borrowers who would answer yes to this question, is at least 65%. That's a threshold. We can do hypothesis testing or build confidence intervals to understand this threshold and answer the question with some standard of confidence. The threshold question gives a hypothesis. Is the population parameter above 65%? Our sample statistic is just one proportion, 70% or 0.70. The null hypothesis answers the question no. The population parameter is 65% or lower. This is a bit different from before, where the null hypothesis was a more definitive negative. There is no difference between treatment and control groups. Here, we set a baseline or a threshold value. In this case, the threshold we are interested in, for whatever reasons, is this 65% threshold. The alternative hypothesis says that the population parameter is indeed above 65. And I'm going to do a one-sided test here, since the research question is specifically interested in whether this number exceeds 0.65. The other side is not of interest, so a one-sided test is appropriate. So we have our hypothesis question and our sample statistic. The question is the same as before. How unlikely is our sample statistic to be a random outcome of the null hypothesis? If it's likely, well then it's not significant and we do not have any evidence for the alternative hypothesis. If it's unlikely, well then it is significant. We reject the null hypothesis and we say that there is evidence for the alternative. The setup for this is the same as before. We can do randomizations and study probability to figure this out. I'll leave the randomization methods aside for now, but we still get a sampling distribution. Under reasonable conditions, the central limit theorem applies and the sampling distribution will be normal. The mean of the sampling distribution will be given by the null hypothesis. In this case, a mean of 0.65. Our sample statistic is 0.70, and we want to know how far out this is in the sampling distribution. Well, that tells us how unlikely our sample statistic is. So we need again to understand the sampling distribution. We already have the mean, since that is given by the null hypothesis. We need the standard deviation in order to figure out how many standard deviations away we find our sample statistic. so that we can use the z-scores and percentiles to calculate its probability, its p-value. For a difference in proportions, this was the formula for standard error. That's the standard deviation of the sampling distribution. This has two proportions and two sample sizes. However, now we only have one group, and happily for us, having one group simplifies the standard error. The formula is just 1/2 of this expression, with only one proportion to worry about. We don't have any pooled proportion to think about either, since there aren't two groups to pool together. Now let me put the whole calculation together. I have a sample statistic, 0.70. I have the null hypothesis, which stipulates a mean of 0.65. I have a standard error calculated by this square root expression, which has the null hypothesis proportion and the sample size. I then have the z-score of the sample statistic, which tells me that it is 2.94 standard deviations away from the mean. And I can turn this into a percentile, which is 0.998, or the 99.8th percentile. Lastly, I can make this a p-value by taking the difference from 1, which gives me the probability that 0.70 or above was randomly produced by the null hypothesis. And this probability is 0.002, which is much less than the 0.05 that is standard, so the finding is significant. I reject the null hypothesis and conclude that, by the evidence of this study, there is evidence that the population parameter is indeed above 65%. Let me make the same note as I did before. In the standard error, the sample size is in the denominator. That means that larger sample sizes means smaller standard error, which means larger z-scores, and percentiles closer to 1, which means smaller p-values. And finally, more likely to find significant results. Larger sample sizes are more likely to be statistically significant, according to the mathematics of probability theory. All right, that's hypothesis testing. I can do the same thing for confidence intervals. The setup is very similar to what we did before, but let me go over it. Under reasonable conditions, I can assume the sampling distribution is normal as before. However, the sampling distribution for confidence intervals is different. I don't have a null hypothesis anymore, I just have the sample statistic. So the sample statistic becomes the mean of the sampling distribution here. The standard error is the same formula, but now I'm using the sample statistic as the proportion, not the proportion that the null hypothesis stipulated. Here the standard error works out to 0.016. That's the standard deviation of this normal sampling distribution. Then the range of 95% confidence was given by this formula, which is still the same here. I go out 1.96 standard deviations from the mean on either side, and the numbers here work out to 0.669 to 0.731. I am 95% confident that the population parameter is between 66.9% and 73.1%. And this also matches the hypothesis test. I am 95% certain that the population parameter is indeed above 0.65, since I am 95% certain that it lies in this range, and that range does not include 0.65. The number 1.96 is for the 95% confidence interval. Other confidence intervals will have other coefficients here, as I mentioned before. And to change your standard of confidence, you just replace this 1.96 with the appropriate coefficient and do the calculation again.